Hello, everyone. This is Cesare Garlati. I'm the founder and CEO of Hex-Five Security, a hardware security startup based in Silicon Valley, California. With me today, I have Sandro Pinto, our head of research and development. Hello, Sandro.
Hi, Cesare. Hi, everyone.
Today, we are going to go through a presentation of the multi-zone secure IoT firmware for RISC-V. And let's start by describing what the problem is. Building secure IoT devices is definitely challenging. We all know there are market requirements that typically involve the design of solution for consumer products. And consumer products typically go in high volumes, but have to be low cost. An additional constraint is the fact that these devices are battery operated, which means that the designer has no really much choice but to use small processors that use less power, but also limited overall hardware, including RAM and ROM. And this leads inexorably to the choice of resource-constrained MCU or microcontroller unit devices. This is great. This is perfect. There are very good products out there, especially on the RISC-V platform. But the key aspect as far as security goes is that these microcontrollers don't have an MMU or a memory management unit on board. They are not designed to run Linux-like operating systems and therefore do not provide virtual memory, which means from a separation perspective, all the code runs with the same visibility on all the parts of the hardware or the SoC more appropriate. Now, in addition to these market requirements, there are some basic IoT requirements. Internet of Things devices typically require a software foundation, which includes typically a multitask real-time operating system, and all the software goes for peripheral drivers. There's probably some Wi-Fi, there might be some radio. Most of the time there is some Ethernet, and then you have USB and you name it, right? Now, this is great. This is not really special of IoT. What's special of IoT is the I in IoT, which is the internet. This device needs to connect. It needs to do this securely. So in addition to that software foundation, what is really required is a set on of software in the form of connectivity libraries. And you're not going to go through the details in this session, but you have to have a TCP/IP stack. You have to have anything that allows that device to go live basically on the customer side, which includes DHCP, DNS, time. In addition, on top, typically for an IoT device, you have something like MQTT, which is the telemetry protocol initially designed by the IBM and now widely used to access really millions and millions of devices through public or private clouds. And as I said, this is a presentation about security. You want to do this in a secure way. And there's really no much to debate about what it takes to make a secure connection. You have to use TLS or some forms of it. TLS is the de facto standard, is what secures any transaction from any device these days. It has to be optimized for resource-constrained devices, by the way. Otherwise, it would not fit these devices. It's been designed for laptops and backends and servers. Big Iron will not run in one of these constrained devices. So you need to use elliptic cryptography, ECC, and some optimized PKI. You want to have a root of trust, but most important, and this is really the core of presentation, you want to have a trust execution environment. Remember, you don't have an MMU. All the code has the potential to break the CIA, confidentiality, integrity, availability of the device and the service that goes with it. So really the issue here is the hundreds and hundreds of kilobytes of third-party untrusted code that you as a designer have to embed in your device, and you really don't know what it is, okay? Now, that was till a couple of years ago, but more recently, we have an emerging number of what I would say advanced IoT requirements, and these are really driven by regulations, right? So access to commercial clouds, secure boot, remote updates, over-the-air provisioning. This is something that is not really a plus. Either you have it or you don't sell your device in that specific region. It's regulated, okay? So the challenging part for a RISC-V, from a RISC-V perspective, is that other platforms, and namely ARM with the Cortex-M competing family of products, have developed some hardware blocks, some hardware capabilities that allow to create the separation necessary to support these new regulatory compliance requirements. Unfortunately, RISC-V have not standardized yet this kind of technology. And this means that implementers, designers are really left how they are figuring out how to put different pieces from different vendors together, right? If they are even available. And so here is where the multi-zone IoT firmware comes into the equation, right? What we have developed under the most permissive really licensing possible is a complete IoT stack. So all the software components, and this shields the trusted applications that are critical, that are core to your service, to your cloud application, from all those hundreds and hundreds of kilobytes of untrusted third-party libraries that you have to put there. It provides secure access to any IoT clouds over MQTT. So it can be public, it can be AWS, it can be Azure, it can be anything. You can run your own servers. You can use our own server, which is public and free out there. It includes out-of-the-box remote application deployment, which comes in the form of secure boot, remote firmware updates, and all the advanced requirements that I mentioned before. But I think what's really going to be interesting for you as a designer is that it works with any RISC-V processor. So what we have developed at Hex-Five is completely based out of the RISC-V foundation standards. There's no special sauce, there's no special ingredient, there's no special design, there's no look-in, there's no proprietary kind of extension. Some vendors have come up with their own attempt to imitate the trust zone kind of approach. We didn't really work well in the market anyway, but that's a different conversation, right? So no need for proprietary hardware or hardware blocks in your SoC. If you have a standard IoT core, that's all it takes. And so here is what you get if you follow this kind of approach, right? You get rapid development because it's all pre-integrated. You have the trust execution environment that supports those regulatory compliance requirements of separation. You have a full-blown TCP/IP stack with many, many services that you can activate and configure. You have TLS optimized for ECC, so perfect for very small devices that need to run keys in a robust way, but with few cycles. And we also added FreeRTOS. And FreeRTOS seems to be really the DOS of choice for many of these applications. There are conflicting opinions about FreeRTOS. That's not our role. The customers have some legacy code typically runs in FreeRTOS. We add this as well. All of this is based on GCC, so it's completely open source, no cost, no price, no licenses. And in fact, we developed this with Eclipse, which again is completely open source. So no proprietary tools, no proprietary hardware, completely open source. All of these models are under a permissive licensing. The built-in trust execution environment provides, in this case, 4 separated wards or containers or areas or whatever you might want to think of. You can have more, you can have less. This is software driven, right? And as I say, there's no GPL contamination. So in no way you will be forced to share your extension or part of your software. In fact, there are no royalties. And the trust execution environment, which is the only part that we actually, that requires commercial licensing, is priced per design. So no volumes, very simple to acquire. So here is a little bit how the architecture works, okay? We cannot go too much into the details in this introductory presentation. So you can find many, many, many more documents and white papers and description of all these blocks online on our website, or also on the RISC-V Foundation various repositories, because we have been kind of prolific producers of content throughout many events, including the RISC-V Summit, all 3 editions, okay? So here is what it looks like once you deploy this. I'm gonna build these slides bit by bit so that we have time to actually describe the pieces. So you start with your hardware. And as I say, that's any RISC-V processor. included in any SoC that you are developing, can be 32-bit, 64. The only thing that you need is the U mode extension or user extension. That's typically something that comes with the PMP, Physical Memory Protection Unit. It's packaged. It's typically a box that you check when you use your designing IDE, depending on the vendor where you buy the IP. But as I said, it's completely standard, and it's a click basically on your design. Or if you buy hardware which is already built in silicon, just make sure it's available, right? So that PMP hardware is what provides the separation, but typically it's not used, it's dormant, it's latent, it's no use, right? And so here is what you do. You add the multi-zone trust execution environment, the TEE. This runs in M mode, which is the highest level of privilege. And what it does, it activates that PMP. So now you're using the full power in terms of security of your RISC-V design. And this multi-zone trust execution environment enable drives that building blocks to deliver a solution that is half in hardware and half in software, which gives you the best of the two worlds, because you have the resiliency that can only come out of hardware, but also you have all the flexibility of being driven by policies, by software. So you can change the security posture, you can rearrange the separation of your device anytime you want. You don't have to redesign a whole new product, okay? So in this specific example, what we did, we put in user mode, which is the lowest level of privilege. The user modes and mode and so forth are defined by the RISC-V specs. You can look into the second volume. There are 4 there. I'm not going to go into the details. As I say, the only thing important for you is make sure there is a U extension there. So in the first zone, we added all of these third-party blocks, put all of them together. And so it runs in one single thread. There's no operating system. It's bare metal, super fast, super efficient, low memory, low cycles, and it controls directly the Ethernet driver. So in the multi-zone architecture, device drivers are in fact executed in secure mode. Otherwise, we don't work, and we just break the whole security separation. And in this case, the Ethernet driver is what is used by the whole communication stack, which includes TCP, then includes the TLS for the securing the TCP, and then MQTT on top of it. In zone number 2 and 3 and 4, in this case, we added a mix of applications, anything from bare metal that blinks LEDs to applications that run in FreeRTOS and so forth. What we do in the demo, I'll mention in a few slides later, is to actually deploy the application remotely. And literally in this case, Sandro will help me from Europe while we are based in the US, so really across the world. And you will see how the application eventually will move a robotic arm and respond to some interaction locally, sending messages over the broker, which is the MQTT server side. Very good. So I just have 3 more slides just to give an idea of what is the applicability of this kind of approach to security. And then I let Sergio and the team there give you a live demo of it, right? So I think the number 1 is really accessing commercial clouds. So typically you as a customer need MQTT, TLS, ECC, and really mutual authentication, which is really important for security, but you need to have something optimized for a RISC-V device. There are other optimizations for other platforms out there. Unfortunately, as I say, RISC-V is quite new, and so this has not been fully developed. We have done all that work for you, okay? And so multi-zone provides the built-in secure connectivity that you need to connect with AWS, Azure, etc. This is standard, no black magic. It's just straight out of the requirement of these vendors, okay? Now, you typically as a customer are concerned about backdoors and lack of separation that results from adding all of these hundreds and hundreds of megabytes of stuff that not even the vendor who gives you really knows where they come. Whether they are open source, closed source, legacy, but I mean, no one writes a TCP IP stack, and for sure no one writes a TLS stack, and for sure no one puts them together in-house, right? It would be a massive effort. And so we have put together these open source components. They work, but you don't have to trust them. They will run in a separate container. Will never be able to affect the functionality of your device at once. And so we provide these 4 separate execution environments. They are hardware enforced. So this is not software magic. It is done by the hardware. You cannot beat it. But it's software defined. It gives you all the flexibility you need. You will see inside. And obviously, you don't want to do this yourself. You could. It takes time, which is money, but also given how RISC-V is on the cutting edge of innovation, it introduced a lot of technology risk in the sense that things might work or might seem to work, but then when someone breaks into your 100 million devices out there, you realize, oh, it didn't really work. That's a risk you don't want to take. Okay, your brain, I'm sure, cannot afford that risk. And so we've done all of this for you. It retrofits any existing hardware and software out there. So we also have version for Linux, but this is not the presentation of today. It works out of the box. There's nothing new to do. You customize for your use, and it's available right now. It's, in fact, is on GitHub for you to try. The second use case, I'm going to go a little bit faster on this one, is really the requirement of firmware updates. Now, firmware updates are becoming more and more mandatory for many applications. But I think what is interesting to observe is that if you can remote update the firmware, you could do something even better. You could start doing remote deployment of individual applications, which opens up a very interesting kind of model, kind of the Apple iStore, where you can just download apps from wherever they come. You don't care. The device is already installed. If even they don't work, they will not break your device. That's the kind of idea, right? So we go under this over-the-air updates firmware, but in reality, you can deploy individual applications. And that's, in fact, what Sandro is going to show you in a second. As I say, high-grade security over-the-air updates. This is as secure as can be, okay? There's nothing more secure than MQTT protected by a TLS protocol these days. Now, if you are concerned about the cost and the security of developing your own do-it-yourself solution, in this case, it's commercial grade and it's available immediately. And again, this is not a porting. This is not stitched kind of patchwork. This is built from the ground. The company has been built from the ground for security, okay? And for RISC-V. So you cannot find anything that would fit better your requirement in this case. And if you're concerned with the vendor lock-in, which is typical of any vendor who wants to push you with their tools and whatever, so a multi-zone remote firmware updates will work with any commercial cloud, but best of all, also with private country clouds. We use open source brokers that we put on an AWS cluster for you. Those are free, but if you want to do your own installation and you run, I don't know, you are a car automaker and you run your own PKI infrastructure, you issue your own certificates for your own cars, that's fine. So we don't need even to know that. And with that, I would just mention briefly the easiest one, which is the real-time monitoring and device management over MQTT. MQTT is the de facto standard out there. You can interact two ways with the device. You can send commands, information. You can retrieve commands and information. And this is done in the most possible scalable way because it's done really for the cloud. Now, this is my final slide. And then I let Sandro give you a live demo. Just give you a little bit of context of what Sandro is going to show to you. So while we start with some reference hardware, this is the most, I think it's the most deployed FPGA board as far as RISC-V work is related. It's absolutely inexpensive. It's $100-something. You can buy it online. The bitstream or the SoC that we put there, it's completely open source, it's permissive, and you can download it from the website. It's a modified version of the original Rocket developed at Berkeley. What this board does then, it connects to the cloud. In this case, as I said, it's over MQTT, secured via TLS, and will receive a couple of applications. One will blink some LEDs, the other one will move a robotic arm, which is locally connected. And Sandro and team will also interact through a dumb console with the device to show the separation. And with that, I'm going to move to Sandro and let him speak.
I hope you are enjoying the presentation so far. What we are going to do now is a short live demo of the multi-zone secure IoT firmware. And just to give you a bit of context of what I have here in front of me. So I have here the Xilinx RT platform born with the X300 bitstream. I have here also the robotic arm and the gateway to connect the board to the internet. just to explain the other connections, I have here the Olimax debugger for flash and debug. Zone 1 will be connected to the internet through the Ethernet cable. Zone 2 is connected to a local terminal. And Zone 4 is connected or will be connected to the robotic arm. Okay? So now I have here the Eclipse IDE, and here we have the project tree, and if you pay attention we have 6 zones instead of 4. The reason is because Zone 3 and Zone 4 are duplicated because the IoT device is shipped with simple stub applications intended to be remotely deployed. That's why we have Zone 3.1 and Zone 4.1. Something worth mentioning is on Zone 1 there is the MQTT config header file that can be used by developers to configure a couple of things in the network stack. For example, if you want to configure a static IP address, you can change it here. If you want to configure a different SMTP server, you can change here. And more important, if you want to connect to a different MQTT broker, you can change it here as well. So this demo, the platform will connect to the Hex-Five broker. So what I'm doing now, I'm compiling the project, which will take a little bit, and then I'm flashing via debug. The idea is to illustrate how easy it is to debug each zone completely independently and completely integrated with the Eclipse IDE. So I'm now debugging just a little bit, and I'm now in the main function of Zone 1, and I can basically use the features that you are used, like step over, step Pinto, putting breakpoints, the disassembly. You can do everything that you are used to. And basically what I'm doing now, I'm resuming the execution, okay? And I'm opening the terminal that is connected in Zone 2. So Zone 2 is locally connected to the laptop, and if you type the enter key, you basically see some commands that you can use to exercise some features of the multi-zone TE. But we are not focused today on this part, we will be focused more on the network stack. So the network stack is implemented securely in Zone 1. What we are going to do now, we are connecting the Ethernet cable to the gateway that will provide a connection to the internet. And we can see that some messages are being sent from Zone 1 to Zone 2 just to report the status of the connection. So this connection is a secure connection over TLS 1.2. And after this message, we make sure that we are connected to the Hex-Five brokers. And basically, to demonstrate that we are connected to the Hex-Five broker, I'm now using the Mosquito application, the publish and the subscriber, just to check the messages that are being sent to the broker itself. So I'm just copying the ID of the client, okay, and I'm now basically writing the syntax of the Mosquito subscriber to basically connect to the MQTT Hex-Five broker using the private keys and the certificates. So I'm now connected to the broker, and what I'm doing now is I'm sending a ping message to Zone 1, okay? I'm using the Mosquito publisher and I'm sending the ping message to Zone 1. And when I press enter, I basically see the ping and immediately I get a pong, okay? So far so good. To get the thing more interesting, what I'm doing now, I'm remotely deploying Zone 3. So Zone 3 has the LED blinking and some interaction with the button. So if I press the buttons, nothing happens because Zone 3 has a simple stub application. But I'm using the MQTT publisher to send the binary of Zone 3 And when you see some garbage in the top right window is basically the content of the binary, and immediately the LED starts blinking, and if I press some buttons, some messages are being sent from zone 3 to zone 1, okay? And to get the thing a little bit more interesting, now I have Sergio here in front of me, and I will ask Sergio basically to remotely deploy zone 4, that is the zone responsible for operating the robot. The idea is to illustrate a customer or a developer that is everywhere in the world, can be in the US or in Australia, and has secure access to that very specific zone and can update the firmware of that zone, and all the remaining system continues working securely and well, okay? So I will ask Sergio to deploy the application, and we will see basically some garbage appearing in the broker. That means that the content of the zone 4 is being deployed. Well, let's wait a little bit, and we saw the garbage. Immediately we received a message from zone 4 that is the ID of the device, which means that zone 4 was successfully deployed, and it basically detected the robotic arm. So I will now ask Sergio basically to operate the robot remotely. So first, to unfold the robot, and as we can see, the robot is being unfolded. And now to send a command that says that is start, that basically emulates the operation of the robotic arm. Okay? So we receive the message, and we see that the robot is basically operating. I will ask Sandro to stop now the robotic arm. It doesn't immediately stop, it needs to come to the initial position because the robot doesn't have feedback. But, well, I think we have clearly demonstrated the value of remotely deploying applications securely, and that we can not only deploy but also operate and send message. I hope you are enjoying the presentation so far. What you are going to do now is a short live demo of the multi-zone.
Sandro, thank you for the presentation. That was a great live demo. And let's complete the presentation today. So the final slide is how you can get started. And so if you want to replicate all of these and take a deeper look, the recommendation is to use this RISC-V board, which I think goes for $120, and you can buy it everywhere around the world. You see the link in the slide. You will need an Olimex debug head if you don't have one to interact with OpenOCD and flash the device. Here is the link as well. And the robotic arm is completely optional. It's a little bit more than a toy, and I think it goes for $100 as well. It takes some time because it's a bash kit. You actually have to assemble it, but it's a lot of fun as well. So not required, but recommended if you want to actually see it in action. As far as the software, all of this is based on open source. So you get Eclipse, the IDE, which is the C developer version. It's called CBT. There is the link. As I say, the bitstream, the actual IP, is completely open source under the most permissive licensing possible. So do whatever you want, basically. And there is the link. We develop it as an extension of an extension developed by Sci-Fi as an extension of the original Rocket core developed at Berkeley. And of course, you need a multi-zone firmware, the SDK, and there is the link as well. We put a lot of effort in writing very good documentation. So there is a great README, but also there is a full-blown manual in case you want to take a deeper look at that. And this would complete the presentation today. Thank you for your time. Any questions, feel free to reach us at info@hex-five.com, or to just look at the many documents and presentations that we have all around the internet. Thank you again for your time.